And now let's look at interpreting the slope of the regression line. So the idea is to take advantage of the fact that slope is a rate of change and interpret in the context of the variables being used. So we take advantage of the fact that slope is a rate of change and interpret in the context of the problem. So first, just a quick reminder of slope as a rate of change. We typically refer to the slope as rise over run. And on a line, if we pick any 2 points on the line, then we can look at the rise, which is how far we go vertically from one point to the next, and the run is how far we go horizontally. If we're given the number instead and we know a point on the line, then we can use the rise over run to draw the graph. We can also just interpret it in terms of the context of the variables. So another way that we hear about rise over run is that it's the change in y. It's the change in the y variable over the change in the x variable. So, for example, a study was run on the relationship between height and weight of adults. A linear relationship was found with regression line y equals -370 plus 8.2x and correlation coefficient r equals 0.76. So again, we have our key linear relationship. In terms of our variables, height is our x, weight is our y. I didn't give units, we'll assume height is inches and weight is pounds. The number next to the x is our slope. The number without the x is our y-intercept. So we have a slope of 8.2. Now, when we talked about the rate of change, we had it written as a fraction, change in y variable over change in x. We can always rewrite any number we want by throwing a 1 underneath. So we have a change of 8.2 in our y variable for every change of 1 in our x variable. So up top, this will be the change in the predicted weight. And down below will be our change in height. So once again, just like with the y-intercepts, predicted is key. When it comes to scatter plots and regression lines, the points don't fall precisely on the line. In fact, it's often surprising if they do fall on the line. The line is just our overall pattern. It's a prediction. So we were looking at the change in predicted weight. So if we put this in a sentence, we could say for every additional one step in the x direction, so in this case, for every additional inch in height, so this is our x units. The predicted weight, the predicted weight this is our y variable. In this case, goes up. We have a positive slope. By 8.2 pounds. So this is our slope. Or our rise, if we don't have a 1 in the bottom. So it's our rise. So for every additional inch in height, the predicted weight goes up by 8.2 pounds. This is the generic sentence. If we do one more, a study was run on the relationship between annual income in thousands of dollars and commute time to work in minutes. The relationship was found to be linear, with a regression line of y equals 85 minus 0.5x and a correlation coefficient of r equals negative 0.62. So again, annual income in thousands of dollars is our x. Commute time to work in minutes is our y. The number next to the x is our slope. So we have our slope is negative 0.5 or negative 0.5 over 1. Negative 0.5 is telling us our change in our y value variable. So this is our change in annual income in thousands of dollars. Down on, oops, sorry, I have that backwards. Top is our y. So up top we have our commute time. So this is our change in commute time. Versus our change in annual income. In thousands of dollars. So what we have here is for every additional $1,000 in annual income, the predicted commute time goes down by 0.5 minutes. So we know it's down instead of up because we have a negative 0.5. So it's the same filling in as the previous one. So the $1,000 in annual income are X units. The predicted commute time is our Y variable. And then 0.5 minutes is our rise and then going down. So this is how we go about interpreting the slope. Unlike the y-intercept, the slope we can always interpret because the slope is just between any 2 points on the line. So we can always interpret it where our data is. All right, that's interpreting the slope.